Okay, we're going to talk about the Biosalvart Law today, and we're going to develop an equation that's probably the most cumbersome equation of the whole year. It's just painful to look at, but it actually, if you take your time with it and think carefully about each little part of it, it really does kind of make sense. So let's review a little bit before we get to it. Here's what we've talked about so far. We've talked about the effect that magnetic fields have on moving charged particles. And we've said that, if I've got a magnetic field, okay, and I've got some kind of moving charge in that magnetic field, okay, that this moving charge will experience a force because of the presence of this magnetic field and because of its charge and because of its motion. And that equation that describes this is the force, the magnetic force, is equal to the charge on our particle times the velocity of our particle crossed with the magnetic field. And this equation is an empirical fact. This is what we observe in nature. And you have to learn how to think this way. Now, if I have a whole stream of particles, a current moving in a wire, for example, if I have a long straight wire like this, and I've got a current running through that wire, and we put this wire in a magnetic field, and in this case it's going into the board. That's what the little crosses means. It means it's going down. Well, this is going to feel a force, and each little moving charge in there experiences this force up here. But when you add up all of those little moving charges, what you get is the current. Well, it's the drift velocity. The velocity is the drift velocity. This right here, this Q, is the total amount of charge that's moving in that wire and so forth. And you can show that the magnetic force on the wire, well, it's directly proportional to the current. The more current you put in there, the more force you're going to experience. That makes sense. We're going to call this L right here, and L is the displacement of, and the direction of L really is the direction of the current. Current itself, remember, is a scalar, but the displacement of the charges moving in that wire is a vector. And this is going to be crossed with B, the magnetic field. And so this is the equation you use to figure out the force on a moving single charged particle, and this is the equation you use to figure out the force on a current in a wire that's in a magnetic field. And then, of course, we took this idea and we immersed a loop of current in a magnetic field. Let's actually make it sideways. So this is all review. This is all stuff we've already done. And we're going to say this has a and this was B. And what we found was that when I apply, this is the magnetic field. This has a certain current running through it. There's I. And again, the source of this current is you got some kind of voltage source in there, and it's got some resistance, so you have some current. We just don't bother to draw that in our picture because it will clutter up the picture. But we just say, hey, look, we got a loop of wire, and we're forcing a current to move through it. And we place it in this magnetic field. Well, when you look at it one line segment at a time, there's no force on here because the L and the B are parallel to each other. When you take the cross product of parallel vectors, you get 0. Then you have here, well, you go, the direction I cross over to B, you get a force that's outward. You have zero force here, and then here the current is going up, so you go I, cross over to B, my thumb goes into the paper, and so that forces this loop down, and so we get a torque on this loop. And what we said was that this torque turned out to be equal to I, A cross B. Okay, this is what we showed yesterday. Now, remember what the A vector is? It's the area of the loop. Here's my loop. Here's got an area, little a times little b here. That's the area. And the direction of the area, by convention, okay, all the physicists in the world got together and said, this is how we're going to do it. You take your right hand and you circulate it in the direction of the current. Let me zoom out so we can get a better view. Here's the current going around, counterclockwise. So I take my right hand and I circulate it in the direction of that, and so my A vector, the direction of my area vector, is outward like this, or out of the paper straight up like this. But if I draw it in perspective, it will come out. And then A cross B, and remember we said that I times A, we define that to be the magnetic dipole moment. That's just a definition. It's a characteristic of the wires, how many wires you multiply it, and all that. So we said that the torque is equal to mu cross B. Okay, and so this is kind of the basics of what we've learned so far about magnetism. But notice that all three of these, we're talking about the effect that a magnetic field has on moving charge. But nowhere have we talked about where the magnetic field comes from. Okay, hey, pay attention. Wake 'em up. Okay, you got to stay with me. I know you guys are tired, but you got to stay with me, because this is where it really is. You're going to have to think, and it does make sense in its own little universe way. Okay, but where did these magnetic fields come from? I mean, when we started, we just talked about having a bar magnet. When we started talking about where. We said, here's the North Pole and here's the South Pole of a magnet, and we've got these magnetic field lines like this. But I just kind of said that. I didn't really say where this came from. So that's what we're going to talk about, is what is the cause of magnetic field? And it turns out to be quite difficult, okay, to understand the equation that we're going to develop here. So we're going to take it one little piece at a time. First of all, let's talk about where gravity fields come from. Gravity fields comes because you got a planet or a black hole or something like that that has a whole lot of mass. Okay? Then we have electric fields. Electric fields, so this is fields. Okay. And how do we make electric fields? What did I do to create an electric field? I separated charge, right? I put some positive charge over here and some negative charge over here, and it looks something like that, okay? Now, gravity has the effect of applying a force to an object that has mass. Okay, so I put a little test mass here, I'll call it m naught, and I measure the field by its effect. But this gravity field is caused by its own effect in a way, in that the gravity has an effect on massive objects, but it's massive objects that cause the gravitational field to be there. Also, we look at electric fields. If I put a little test charge right here, it's going to be pushed by the electric field. So that's the effect of the electric field. But the cause of the electric field was also charge. The gravity field has an effect on mass, but mass is the cause of the gravity field. Electric fields have an effect on charged particles, but it's charged particles that cause the electric field. Okay? Now we're going to talk about magnetic fields. Magnetic fields. Well, what is the effect on? The effect of a magnetic field is on a moving charge. Okay, so here's our charge, and it's moving. And I've got some magnetic field here that's going to apply a force to it. So if the effect on the moving charge is a force, what do you think the cause of the magnetic field is going to be? Huh? Exactly. Other moving charged particles. Okay. The cause of a gravity field, well, its effect is on mass. The cause is mass. The effect of an electric field is to apply a force to a charged particle. But the source of that electric field was other charged particles. Magnetic fields, it's the same thing. The effect of a magnetic field is to apply a force to a moving charged particles, but the cause of it is moving charge. The cause of this magnetic field turns out to be moving charge. Okay, and these guys named, Jean-Baptiste Biot, I don't know, B-I-O-T, how do you say that in French? I think they were French guys. Is it Biot? Isn't the T silent or something? I'm just doing my Steve Martin, French accent. And then Biot-Savart, I don't know. Anyway, these two scientists worked together because they were seeing, magnetic fields deflecting compass needles and applying forces and so on. And so they did some experiments, and this is what they came up with. Okay? If you have a current, that is, if you have moving charge flowing through a wire, or anything, doesn't have to be through a wire, but the simplest example is it moving through a wire, that's going to create a magnetic field. So let's take a look at and this is the Biosalvart Law, and these were two guys that worked together to figure this out. Here's what they came up with. Let's just take a look at some random piece of wire. Okay, and let's say it's got some current flowing through it. Now, to keep things simple, we're going to say this current is constant. Now, what they discovered was that if you have a current, it creates a magnetic field. And hey, this is consistent with the other two fields that we've dealt with so far. So let's take a random, let's just look at a point in space like this. And what we're going to do now is we're going to look at a little tiny part of the current, a little tiny displacement of current. So let's take a look right here. So here's my current I flowing through here, and here's a charge that's moving, and it moves through a little tiny displacement, ds. So what does ds represent? ds represents the displacement of charge, how much it moved. Okay? Now it's going to take time to do that, but it doesn't include the time. It's just a little displacement, and it's an infinitesimal displacement. Well, this displacement of charge right here is going to create a magnetic field right here. And here's what we've discovered. This little tiny displacement of charge creates a little tiny magnetic field up here at this point P. And here's what we expect. And it actually works. This current is causing the magnetic field at this position in space. Now, wouldn't you expect that the greater the current, the greater the magnetic field that current causes? Yes. So it turns out to be directly proportional to I. Okay? And also, it also depends on the amount of displacement you have. Now, what we're going to do is we're going to integrate eventually, but wouldn't you expect the longer the wire to be, the more magnetic field there is? Yes. So it does depend on the length of the wire, which is represented by ds. Now again, we're going to integrate over the whole length of wire to get the total magnetic field at that point. But for right now, we're just looking at an infinitesimal piece of it. Okay, now let's take a look at this distance here. This is how far away my infinitesimal little displacement is along the wire. This little tiny piece of the current is from my location in space. We're going to call that R. Now think of this. This is going to be kind of weird, but you have to think weird when you're dealing with magnetism. Think of it as a point current. Remember we had a point charge or a point mass? When we had a point charge or a point mass, didn't the field decrease by the square of the distance? Right? If you were twice as far away, you had 1/4 as much gravitational field or electric field. Same thing is true here. If I have a little tiny point of the current, a little tiny chunk of the current that I'm looking at, and I'm trying to figure out how much magnetic field it causes over here, it turns out to be over r squared. That is, if I make this point twice as far away, if I were to take this point in space and put it twice as far away, it would have 1/4 the amount of magnetic field. Okay? So this actually is following the same pattern I've seen in other, we've all seen in other kinds of fields. Okay, now comes the direction of the field here. And this is observationally derived. The direction of the magnetic field, if the current is flowing like this, and this is the direction of the displacement of the current, right? The magnetic field is going to be out of the paper. It's going to be, at this point, on this plane, it's going to be pointed outwards. Now, how do we say that? How do we figure out, how do we show that it's outwards? Well, I'm going to call this r hat. This right here is a unit vector. And it just says, in the direction from where my current is to that location in space that I'm examining. I'm trying to measure the magnetic field for. Okay? If I take the cross product of ds crossed over to r, ds cross r, notice my thumb is coming out of the paper. Let me zoom out so my hand isn't so big. I'll zoom back in a minute. But I go ds cross over to r, it's out. So this is coming out of the paper. So we go cross r hat right here. Now this part right here, this ds cross r hat, It's there so that I can just, this cross r hat is only there so that I can describe the direction of the magnetic field. So now the magnetic field is a vector. Remember that r hat has no dimensions with it. It has a magnitude of 1 and it's dimensionless. This does not have any units. It's not in meters. R hat is not in meters. It just describes a direction purely and only. Now, this is the only thing I can do to vary the magnetic field at this location in space due to this little tiny current right here. I can vary the current, I can vary how far away it is, and I can vary the length of the wire, and that's it. But now remember over here, I had to figure out what the gravitational field was. I had m over r squared in the negative r hat direction, right? But what did I need out here in front of it? I needed a constant. And then over here, for a point charge, I should have drawn this as a point charge, shouldn't I? But for a point charge, I said that E was equal to Q over R squared in the R hat direction. But what did I need out here in front? A K. Well, that's exactly what I need out here, is a constant of proportionality. And it's the weirdest constant of proportionality there is. And it drives students crazy, but I'm just going to have to tell you. The constant that's going to go out here, well, it's going to be mu naught over 4 pi. Exactly. If you're making that Scooby-Doo sound, I don't blame you. That, why call it mu naught over 4 pi? I'm just going to tell you, remember when we had K and we said that that was 1 over 4 pi epsilon naught? Okay, because later on it became convenient, when we used Gauss's law to express it in terms of this constant right here. And we called this the permittivity of free space. Okay? And we just kind of left it at that. Well, we express it this way because this mu naught right here, mu naught is called the, am I still on screen? No, barely. Is called the permeability of free space. Now, free space means it's a vacuum. This mu can vary in different materials. We're not going to deal with that in this class, but you will in later classes probably. It's a measure of how easily magnetic fields flow through space depending on how much current you have. It's the same thing as big G. How easily do gravitational fields flow through free space? How much gravitational field do I get, for a certain amount of mass? This is how easy is it for an electric field to flow through free space? It's a function of our universe. It's a characteristic of our universe. And this does the same thing for magnetic fields. Okay, so now it has a value. It has a very strange value. It's 4 pi. Ooh, look, there's a 4 pi on the bottom. Times 10 to the negative 7. Now, let's think about what units mu naught has to have. Because what units does magnetic field have? Well, it has units of Teslas. So we want to end up with Teslas, but then what do we have to cancel out? We have to cancel out the amps And then I also have to cancel out the, let's see, I've got a, well, let's take a look here. I've got a meters right here, and I've got meters squared down there, and I've got amps right here, and I want to end up with Teslas. So this will cancel that, and I want to get rid of that 1 over meters, so I have to have a meter on the top. Oh, sorry. So the units it has, mu naught has the following units. Tesla meters per amp. Now, you think that's crazy. All right, well, you know, you're just learning this stuff for the first time, but think about it. What units did G have? It had Newton meter squared per kilogram squared. Why? So that we could get newtons there for Newton's law of gravity. K has units of Newton meter squared per coulomb squared, so it cancels out to give us newtons. This cancels out the same way so that we can have Teslas. Okay? So now this is the Biosalvart Law. Let's just rewrite it down here. So dB is equal to mu naught over 4 pi. This is just a constant of proportionality. It makes all the units work. Now notice the 4 pi cancels and you get 10 to the negative 7. Now that's because the way Teslas are defined, it's based on this magnetic property of nature. So this right here is an exact value. This is unlike the other constants of nature. We've defined magnetism in terms of mu naught. So this is actually an exact value. It has infinite number of significant figures. Times I ds cross r hat over r squared. Now, of course, what we really want is the total magnetic field at this point due to the whole current. So what do we have to do? We have to integrate both sides. And so we get B is equal to mu naught I over 4 pi. Because what we're going to do in this class is we're going to do this for steady currents. The current is going to be constant everywhere. Believe me, this is going to be hard enough. Times the integral of ds cross r hat over r squared. And this is the Biosalvart Law that we're going to use. The good news is we're not going to use it very much. We're going to use it to derive a few very special situations that are relatively simple, and then we're going to use that to we're going to use those other things to use laws that are much more. We're going to use this to develop Ampere's law, which we're going to do on Thursday. Okay, so what we're going to do next is we're going to do an example problem of this, but I want to break these videos up, so we're going to start that in just a second.